Hi everyone, in today's video we'll specifically explore SageMaker Inference and the different hosting options that are available within it. And before we even get to SageMaker itself, what we'll do is we'll talk about what machine learning inference itself is, what does it entail, what exactly do I mean when I'm saying that, and then we'll also talk about the different machine learning inference modes or deployment modes that exist there. So in the ML kind of world, right, there's many different use cases and there's many different requirements for the specific use cases that you might have. And what we'll specifically do here is we'll map the different SageMaker inference options or hosting options to your specific use case. So depending on your requirements that you might have, you'll come out of this video having an understanding of what SageMaker option, right, for hosting specifically is best fit for my use case. And SageMaker is not necessarily just an inference or hosting platform. It's a completely managed ML service. So it covers training, MLOps, monitoring, inference all included, but in this series at least we'll specifically look at just the different inference or hosting options, which I've listed out here. And in future videos also we'll get hands-on with each of these so we can work through the code for all of them as well, just so you can understand how it works. And we'll also explore more advanced hosting options like this last bullet here around multi-model hosting when you might have multiple machine learning models that you're deploying on a singular endpoint. But we'll get to that in a little. What I'll do right now is I'll quickly open up the iPad right here and jump into the whiteboard, and what we'll overview is kind of some of these talking points that we just highlighted here. What specifically is ML inference or hosting, right? And I'd like to quickly revisit, and if you've seen some of my earlier videos you can skip this, but I'd like to quickly visit the ML lifecycle itself, right? Within the ML lifecycle there's many different components, and at a high level what you can imagine this as is your data prep or kind of your engineering that you might be working with. You might then have your model training that you're essentially working with. And from the model training, you might deploy your model right here. Deploy your model. There's also eval/monitoring that you might work with at different times. And you can then go to kind of repeat this cycle. This is a very high level. I'm missing probably many parts / there's a lot of depth to each of these steps that I'm simplifying here. But you can think of this as a general ML life cycle, right? A really key part, or where machine learning is really realized, is in this deployment step. And just to clarify, I keep saying deployment, hosting, inference. You can think of all of these as kind of the same thing. I use them interchangeably, at least I know some people might be more specific on jargon. But think of all these three things as kind of the same word, at least in this context. But in deployment, right, the practice of deployment is essentially once we have our trained model and model weights, which is essentially the state of the model, and we're happy with the kind of data science accuracy or performance of it, we would like to expose this, right? We need to expose this because what good is the model if we can't use it in our application or expose it to our end users? So the practice of kind of exposing it as a REST API to your end users, right, is what ML model deployment is. And you can think of inference, once again, very similar things, or almost the same thing in this context, as when a client sends in a request to your model and it returns a output, right? This output is your model inference, essentially. So all these words you can use as similar, but this is really where the value of machine learning is really, or machine learning models are really realized, because this is how you can bring them into your overarching applications or use cases that you might be working with. Now, what are the core building blocks behind deployment itself? So, deployment, core building blocks. Because I'm about to introduce a lot of different options that exist, but kind of the fundamental pieces stay true no matter what in terms of what you're working with. You might manipulate them or adjust them a little depending on your use case, but there's a few things that will always stay consistent. One, and first and foremost, is hardware. Now, this might not seem that crazy if you have a small pet like scikit-learn model that is maybe a few MBs in size or something that you're dealing with. You can actually load this probably locally on your Mac or PC, wherever you're working with, and just have a server such as Flask or Fast API and use it to kind of serve that model and load that model with the compute that you have available on your local PC. But the problem is, as models sizes kind of get bigger, this becomes a challenge, because if we think about LLMs, right, we know some LLMs that are greater than 50 GBs in size at times even, right? So the reason we need to think about compute here is we need the memory space to be able to kind of load this model into memory. And that's where thinking about Do I have GPUs or CPUs? Or there's also custom chips that are constantly being developed by different kind of companies to host these models more efficiently. But we essentially need the compute that has the kind of juice to be able to host these models and work with these models. And it's not just the models, right? Like I said, in a sample pet use case, it might just be you sending the request to your model that you have loaded up on your computer's memory that you're working with. But let's say that you have thousands of people, and oftentimes the scales to even more, right, for use cases such as ad tech. Let's say you have thousands of users that are hitting your model concurrently. You need to be able to have the compute where you can really scale up the workers that you're working with, essentially, to be able to handle that traffic. So that's where hardware is really important, because we need the power to be able to work with this work with this model as the sizes increase, and we also need to be able to handle traffic increasing. And then the second part, right, it's important to have hardware, but it's not going to be effective if you don't have a smart model server there. So you can think of the hardware as kind of the muscles or kind of the physical juice behind everything. The model server is almost the brains behind the operation. So what a model server does is, right, it has access to these different things. It says, okay, here's my compute that's available. Here's my model that is essentially that I'm working with that we've provided here. Here's my model's weights. And it can also depend on whatever framework that model might be. Keep in mind, machine learning models have different frameworks such as PyTorch, TensorFlow, Onyx, whatever else you're dealing with, essentially, right? So your model server has all this different information. The computer has access to and your model's weights, essentially. What the model server does is it intelligently exposes different things for ML engineers such as ourselves can tune, essentially, to optimize for performance. What I mean by this, right, is let's say that, for example, there's many users that you're working with, kind of as we were alluding to here in this use case here. It exposes things such as enabling for you to deal with concurrent traffic. So it has an idea of the compute or the number of workers that are accessible to you, and you can scale this in and out depending on the traffic that your model is essentially receiving. And this feature, the flexibility of that kind of varies depending on the model server that you're essentially working with. But you can think of model servers, they essentially give you the capabilities of being able to handle concurrent requests hitting your models, because you can essentially tune the worker count that your model has at the model server level itself. And the reason we're able to do this is the model server has access or knowledge of the compute that we have. The model server also helps with other things such as kind of loading the model in and out of memory. So it takes care of operations such as that. It exposes this model as a REST API. And like I said, it also lets ML engineers such as us, right, who build kind of familiarity or experience with these different model servers to tune different parameters. So on the server side, you can, for example, queue requests. You can tune things such as the worker count, and this is where I was alluding to the concurrent traffic, if that was a little unclear earlier. But you can essentially tune things to optimize the latency and throughput as your requests are coming in, because the model server intelligently, right, has all this logic basically baked in. So it handles a lot of these different things for us at that layer itself, at the serving layer itself, because it knows how to work with the hardware that we're essentially using to host our model. And using this, right, once again, think of this as the brains behind the operation, and the hardware is the physical compute or juice. And the interaction between these two, right, the model server knowing how to use the hardware to efficiently host your model and handle the requests that are coming in on the server side, right, from your client, that's really what powers high performance machine learning model hosting or deployment. And different model servers, right, that you might hear of that are popular, and like I said, each of them have their own nuances or languages or protocols, and we'll dive into those later, so don't worry too much about the nitty-gritty there. But some of the stuff you might hear of are TorchServe. NVIDIA has something known as Trend Inference Server, and then Amazon has something in-house known as DGL Serving, and there's also TensorFlow Serving as well, and many more, right? This is a constantly kind of evolving art as the models also mature. So the main key here, right, is it's the conjunction of these two that leads to that high performance hosting that we're talking about. And these building blocks exist regardless of whatever ML use case you're dealing with. You're going to need the hardware, and you're going to need the model server that knows how to load whatever model you're working with, or work with whatever model you're working with, efficiently on the compute that you're also selecting for it. Now, I keep saying the term use cases, right? Different use cases. And what I mean by this is, right, within the ML application world, there's different options that you might be working with. And there's two buckets that these oftentimes really fall under: offline and online. And people can name this differently. Once again, this is just a high-level overview of what we're looking at. With offline inference, right, a sample use case, right, let's just say you have a bunch of documents and you have a model, a summarization model, that you want to run on those documents on a monthly basis. So at the end of every month, we're going to pass in these documents to our model. We just want to output back. We don't really care about latency. Don't care how many documents, like throughput maybe, that we can squeeze out per second. We're not really thinking about all of that. We just have a model. We're going to dump like a batch of like kind of inputs into it, and we just want our output back. We don't have any strict latency or throughput requirements. When you have a use case like that, basically, and document summarization is a popular one, that is known as an offline use case. Online, right, is, let's say you do care about those things where you have latency and throughput requirements, where you need I like to use the word instantaneous response to a request for your model, right? You need a response very quickly, and you need that model to essentially be accessible whenever you do have a request. And examples of this, right, include chatbots. So if you're, for example, using ChatGPT, right, you expect a response back as soon as you have an input query or things of that sort. Other examples include ad tech use cases, personalization use cases, and then even things such as recommendations, right? So if we need recommendations generated. These are all online use cases. So you can think of online as, I think the key word here is persistent, or we can even give a second word, persistent and readily available, right? Whereas offline is, you just have your input and you want to get an output. You don't really care when it comes, as long as you can process all those input requests that you want coming in. And this is really where you want to think of, right, when you have an ML problem or challenge, what use case makes more sense for me and what exactly am I trying to achieve? And that's a key thing that everyone should take into consideration when baking an application, right? Because if you have these requirements, right, you need to think of how can I achieve these and what's the right hosting option for it. So try to really visualize these two buckets whenever making a ML application decision or choice. And to address that, right, what SageMaker specifically did was launch 4 separate hosting options, and kind of pre-wrote this just so it's a little clearer ahead of time, but there's 4 different main deployment modes that you can essentially work with within SageMaker Inference specifically, right? And in these deployment modes, what we have is 3 endpoint-driven options, as you can see here. And you can think of this as a REST endpoint that we're exposing. And then there's an option known as a transform job. And we'll talk about what the online and offline use cases are one by one here. The first option I want to highlight here is real-time inference. Within real-time inference specifically, right, this is your most low latency, high throughput sensitive use case. You have a persistent REST endpoint. You can back it by selecting a CPU or GPU instance, and you can also auto-scale your endpoint or attach an auto-scaling policy. So you can say if more requests are coming in, scale out my hardware to have n number of instances, and scale down to 0, for example, if my application can tolerate that. But this is your use case, right? This is your option to use whenever you have something that needs a response as fast as possible. So use cases specifically for that include like most of the online ones we've alluded to. Ad tech, chatbots, recommendation engines. These are all real-time endpoint-driven use cases. A second one that also fits under online inference is serverless inference. And just for quick clarity here, right, when I say endpoint-driven options, it's all three of these. Real-time, serverless, and asynchronous are all REST endpoints that you can essentially invoke by yourself. And here, serverless inference, the second of the online slash endpoint options right here, is essentially a use case where you mainly don't want to select or manage the hardware behind it. If you notice within real-time inference, you're still selecting a CPU or GPU. Some people don't want to have to do that, so they let the scaling happen beneath the scenes by the SageMaker service itself. And this is similar to other serverless services such as Lambda and things of that sort, and there's also provision concurrency support to kind of help mitigate cold starts. But you should pick this option, right, if your application is not as latency sensitive as a real-time endpoint would be, and you can tolerate a bit of a cold start. So it's still a use case for online where you need an endpoint that's available to serve traffic. But keep in mind, since you don't have persistent hardware behind it, at least exposed to you, that you've chosen or selected, it might take some time in terms of that cold start response. So you need to keep that in mind when picking between real-time and serverless, essentially. And that's a common paradigm, whether to go the hardware route or the serverless route. So you want to evaluate that. The general rule of thumb I at least think of, right, is as the concurrency itself increases, there reaches a point or a midpoint where real-time inference is actually cheaper than serverless at that point. So you want to do the calculation of, should I just select my own hardware and optimize it with the scaling policy, or should I go with serverless inference where I'm not really thinking about the hardware, but my latency might not be as good as expected, and if throughput really increases or my concurrency increases, then I might actually end up paying more. So those are the types of considerations you want between those two options in terms of the trade-offs. The third and the final endpoint option is asynchronous inference, and this is also a near real-time use case, and honestly you can kind of maybe batch it. You can think of this as a bit of a marriage between online and offline, and I'll explain why in a second. But here with asynchronous inference, right, there's a managed queue that's provided for you. So if you have use cases where you want to be able to queue the requests, I believe it uses SQS underneath the hood, essentially. You can fit requests into that queue as you're processing the existing requests, and you can also enable auto-scaling similar to real-time inference and scale down to 0 with both, at an added here, CPU and GPU instances here. And this is really good, right, for use cases where you might have a lot of processing time or heavy processing time. So if you have video processing or video streaming that you might be dealing with, or object detection where you might need to queue future requests because your model is currently processing the existing requests, this is very fit for those types of use cases. So you can essentially think of this as near real time. I still want an endpoint to be able to invoke, but I also might have an offline use case where I can scale down to 0 and I'm not that latency sensitive, and I have long processing times for each of my requests. Because here, a real-time endpoint, right, I didn't add this, but I'm going to add it just for your reference here. The timeout period is 60 seconds. So if you send a request, that request needs to be returned in 60 seconds with the real-time endpoint. Whereas for asynchronous inference, in the documentation, we'll have the exact value, but that value increases substantially, right? So you can have longer processing times. So think of these three as your endpoint options that exist within SageMaker Inference, and serverless and real-time are specific more for online use cases. Async, you still have a use case where if you need the endpoint to be hit, you can, but you can also optionally use it as an offline option because you can queue requests and scale down to 0. So it's not that latency sensitive, if that makes sense there. Now the purely offline option here is batch transform, and within batch transform you don't have a persistent REST endpoint. It's something known as a transform job where you basically say, here's my input data, this is my model server / container that I'm working with, this is the compute that I want behind it, and this is where I want my output data to be dumped into. So there's no REST endpoint that you can essentially just invoke whenever you feel like. You just have to kick off a transform job, provide your inputs, the model metadata. Like I said, those two objects that we were talking about earlier, right here, this information will once again stay consistent across all these modes. So you provide that for each of these, but you also provide it specifically for batch, along with that same input data and your output data location, essentially. And different use cases for this, right, might be document summarization, as we were alluding to, any kind of offline processing jobs that you'd like to think of where you just have an input set of data and you have an output set for where it needs to be dumped to, essentially, within a certain cadence. Those covers kind of the different use cases that we're dealing with here within batch and the different deployment modes that we have. What I wanted to do really quickly to just kind of end the video was go into the console real quick and talk a little lightly about what exactly we're looking at. So if I go here within SageMaker AI, that's what it was renamed to around the reInvent time period. If you look here, specifically within Inference, this tab here, you can notice that there's a few different options. I don't have any of these up and running right now, but you see the two separate hosting options that we were talking about. You'll see that there's endpoints, and this is basically where you can create the endpoint of your type that you're choosing here. And you have different batch transform jobs that you can essentially kick off. And if I click it here, right, you'll see some of the parameters that I was talking about. For example, the model, the compute that we need, the input data and output data location. And the key takeaway here, right, is these objects above that you're seeing here. This is those two kind of resources that we were talking about earlier. So when I was saying the compute, any auto-scaling related to the compute, and then also specifically that model data or weights and that model server / container that we were alluding to, those objects or constructs, right, they stay consistent regardless of whatever hosting option you're using. So when you come to SageMaker Inference, there's obviously different options, but the core building blocks, which is these two objects right here, the models specifically, this is something you have to create whether you use batch, async, serverless, or real-time. Obviously, endpoint config is more specifically for endpoints, but this here captures those two core pieces that we were covering in terms of what model deployment or hosting is. And that's going to stay consistent regardless of whatever hosting platform you use, whether it's SageMaker or elsewhere. You need a model server to be able to work with the compute that you're essentially going to back your model with. And I think that's what I mostly had in mind for today's video. Like I said, what we'll follow up with is across all these different inference options, we'll give code samples, walk along specifically for the theory behind each, and show some more of the smaller nuances that you'll have to get familiar with. And in the meantime, what I'll also do is I'll add a Notion page, as always, underneath in the description link, basically here. And I'll make this public for you guys, so where you can just see the different kind of code samples if you want to just get started beforehand. You can see the documentation specifically for each of these hosting options, because there is a lot, so I can see how it's overwhelming. And as I also said, we'll cover this in this series as well. If you have a use case where you have multiple models, we'll talk about the most efficient way to kind of host all of this together. I'll host all those models on a singular endpoint, sorry. But yeah, sounds good. And I think any feedback that you might have, any questions you have, feel free to please leave it in the comments as always, or reach out to me directly on LinkedIn or Twitter. And if you like the video, please do give it a subscribe and a like, and I will be back soon. Thank you all.